All right. One thing that we didn't really talk about previously when we were at least in 364, we were talking about heat exchangers, is this idea of mixing versus not mixing. So in this example, we're looking at a cross-flow heat exchanger. When you have a cross-flow heat exchanger, you can have a situation where either you allow the fluid, say on the air side, you allow that fluid to mix with itself as it's going across the heat exchanger, or you can force it to remain unmixed. And that has implications for the thermal profile. So why is that? Well, if we look here, let's look at, here's our cross-flow heat exchanger on the top, right up here. So on this, let's call this the, maybe the hot side. So let's say this is an air conditioner. This is our hot side. We have a flow going through on the hot side. And then down here, we have cold air that's coming through. So if you allow, or if you don't allow fluid to mix in this direction, or you don't allow the air to mix as it's going across the bank of tubes, what would you see if you were to plot the temperature? Here's our, let's see, 2D, I'll zoom in a little, 2D temperature plot of this device. So we have cold fluid coming in here. And remember, we're not allowing this fluid to mix. So as it goes across the heat exchanger, it's going to start heating up that fluid. And eventually it comes out over here. So if you're that bit of air that's coming in right where the fluid is hottest, right, this is your delta T. And as you move along, your delta T gets smaller and smaller, and you end up kind of converging with your final outlet temperature up here. This is unmixed. So over here, you can do the same thing, but your delta T is pretty small. And so you're just kind of moving these both up in parallel as you go out here. But you'll notice that there's a big difference between the outlet of the fluid depending on which side of the heat exchanger you're on, right? And that's because as you go through, you can't perfectly mix the fluid. You can't get it to some uniform temperature. If it's mixed, however, so let's look at this example now. So now let's say my cold fluid is here. So this is cold. This one here was cold. So my cold fluid comes in, and I'm going to make the assumption that as I'm going over the tubes, there's enough going on there that the fluid is perfectly mixed. It's maintaining a uniform temperature as a function of, say, this direction. It's uniform, but it's not uniform as it moves across the bank of tubes. Then what you see is something more like this, where you still have coming in here hot versus cold. And those will have to converge to something as they go along. But you notice that this, if you pick any specific position here, the temperature is actually uniform across the entire width of the heat exchanger. So this is, it's a slightly different solution. It's not as different, it's not the same degree of difference from this to say parallel or counterflow, but it is an important distinction, and it can lead to a different solution. So when you're using those cross-flow heat exchanger correlations, you're going to want to keep in mind, okay, is my fluid mixed? Is it unmixed? Often it's actually somewhere in between. So you have maybe a mixed situation, but you don't assume that there's perfect mixing. So you might use this correlation, the mixed correlation, to get you a bound on the system, but it's not actually the perfect actual solution. So like, let's say on the outlet over here, there was some like header where they.
Yeah, like the first port on the top and like a header top port.
Yeah, so that is really common to do that. So you come in, you have some header, it distributes over. So you'd assume by the time it gets over to the next pass that it's a mixed temperature, and every tube going in this direction is going to be coming in at a uniform mixed temperature. But as you're going through along here, it's not. Right. So now that gets into maybe you come up with a model where you solve that first block, and then you mix the temperatures, and then you solve the second block. And you have this maybe multi-pass type heat exchanger model, where you're modeling each pass separately in sequence. Or a lot of times, people just do empirical correlations and use that instead. Any other questions on that? Okay. So that's mixed versus unmixed. Again, there's correlations for those. We'll look at those in a second. At least I want to. Let's see, actually, where do I have that? Maybe we could. I'm going to start these now just to have it. But we'll keep talking here as we get that up. Okay. Okay, so one other thing that, one other geometry is kind of exactly what the question was about, is this, we call it shell and tube heat exchanger. And then this heat exchanger is hard to see. Let me zoom in. So in this heat exchanger, this is actually really common in power generation applications. Like if you have a steam generator or a boiler or a superheater or something like that, where you have some fluid. This is an example from concentrating solar, which is something I've worked on, where you have molten salt to steam heat exchange. So you have one fluid coming in, let's call it here. So we have coming in here, we have our molten salt. This is the thing that's supplying heat to the power cycle. So it's coming in really hot. It's going on the shell side, but it's kind of at a local position going at a cross flow arrangement. So it's cross flow with a bank of tubes. So in here, in each of these tubes, we have steam going through. We have salt exchanging with steam in a cross flow arrangement. At the top, there's this baffle. This baffle is kind of separating these regions. So at the top, the salt comes in and starts crossing over. So you go from a counterflow, or sorry, a cross flow arrangement to then either parallel or counterflow, and then it switches back to crossflow and goes up and down and up and down all the way around the full system. So this becomes a really complicated heat transfer problem, but from a practical or kind of a construction standpoint, this is often done. If the point is just to get steam in these tubes to boil, which is happening pretty much at a constant temperature, you don't really care whether the local temperature is what it is. You just are trying to add heat from the salt. So in this type of arrangement, you're seeing this, say water is coming in here, it actually goes down, does a U-turn and comes back around like this, or the other way around. It's in this direction. So it's doing a U-turn coming back around. Meanwhile, you have salt crossing up and down over both of those flow paths. So this becomes a really complicated thing to model. In fact, I was advising a PhD student when I was at NREL. He spent almost 4 years developing a CFD model of this specific geometry. So it's a really challenging thing to do. But in the end, depending on what you're trying to do with it, there can be something you use a correlation for. So there are correlations in ease. They look something like this. You might go in there and put in, okay, I have a shell and tube. My shell has 1, 2, 3, 4, 5, 6, 7 passes. So you'd specify the number of passes that it has, or sometimes those would be like, maybe it'd say 1, 2, 1, 2, and 3 passes. You have to look at the correlation itself. But this will give you some empirically derived correlation that you can use to predict heat transfer in this particular geometry. Yeah, so here's a cutaway of an actual CFD of these. So you have these tubes that are going through these baffles and kind of complicated flow. So I won't ask you to model these directly, but you probably want to use a correlation on that. Okay, yeah. So hopefully not a lot. I mean, the correlations should be pretty good. The reason why you might want to do a CFD analysis is, let's say, well, in our case, what we were trying to do is model the transient behavior, non-steady state behavior. And the correlation is not going to do that for you. So we needed to understand when you actually go to start up this plant that has salt and steam in it, if you don't do it carefully, there's a lot of thermal stress induced in that system. You can see like there's these baffles and they're all fixed and there's high pressure involved. So what we wanted to do was get a really detailed model, validate it against the correlation, and then use it for something new, which was the the transient part of it. So the first 3 years, we're just trying to get it to validate. And then the last, what was the actual new part? Is usually how things go. Good question. All right. So let me, let me pull up ease, I think, here. This is a good time to do it. Let's look at some of the correlations in ease. So if you want to use heat exchanger correlation, one way to do that is to go in here in the function information. We go to heat transfer and fluid flow, and then in the drop down, there are heat exchanger correlations. So we'll get to some of these correlations later, or what this NTU effectiveness thing is, but these are all going to be here. These relate the performance. The other thing that I'm going to talk about a little bit here, we can show it now, is this compact heat exchangers. You probably have not used compact heat exchangers before, but the compact heat exchanger library is all here. If you know that, say, your heat exchanger has fin circular tubes, maybe it's a fin plate with louvered tubes or whatever it is, you can come in here and actually pull out specific correlations. So you could look at fin circular tubes, and you could flip through. And it's really hard to see it here, but there's actual, so CF, what is it, CF-7.34. So this is an actual heat exchanger geometry that you could go buy off the shelf. If you wanted to model it, you could come in here and do so, right? So you come in here to your compact heat exchanger library. The first thing you're going to do is you're going to get the actual geometry. So you see there's these different subheaders. This is a little different from libraries that we've used before. So there's subheaders. The first thing is let's get the geometry. So if you look at this call, what it's actually doing is it's taking one input, and that input is the name of the thing I'm trying to get. It's CF7058J. That's my heat exchanger. It is going to return for you after this colon. It's returning a bunch of stuff. And what is it returning? Let's stick here. It's returning. Returning a bunch of geometry that has to do with this particular heat exchanger. So the tube diameter, the fin diameter, these different geometric parameters, ST, SL, the pitch of the fin thickness, and so on. So this is being all set by this call. So why is that helpful for you? Well, it's helpful if you have other functions that use that stuff directly. So we go back to our compact heat exchanger. We started with geometry. If you scroll down a little bit, you'll see there's this label non-dimensional. So in the non-dimensional section, that's actually where you get back. That's actually where you get back the performance of this heat exchanger. So now I'm giving it. What did it do? Try this on a new line. So now I give it the same name of the geometry here. And I also have to give it the Reynolds number of flow. And this, it'll tell you how to, correlation will tell you how to calculate the Reynolds number for this particular geometry. And it gives you back two things. It gives you back this F, which is the friction factor, and it gives you back a J. And so J is what's the Colburn J factor. Let's see if I had yeah, we'll get to that in a second. So the Colburn J factor is the sort of way these heat exchangers are normally described, but it's, again, not a physical quantity. It's something you have to convert. So the next step would be in the same libraries. Let's go back and let's say I now want to get my convection heat transfer coefficient. So I come in here, again, find my same thing, and I paste it in. And now I can take as an input the characteristics that I'm solving for, and it will then decode this J factor directly here in terms of the heat transfer coefficient, which is actually what we care about. So this is maybe something I don't think probably should go through in detail and try to do it, but it's something that at least I want you to know where it is in the libraries. It's there. At some point, if you need it, you can learn a little bit more about it, but there's these different steps to using the libraries, and that's really all you need to know. Often in industry, this is kind of a complicated process, as you can see. It's not something where you just go look in a table and it's there. it's a little bit more complicated. So in industry, what people will do is, if you're a entry-level engineer, you might call the manufacturer and say, how does your device perform? And they'll say, well, it performs like this. And then you take that and you plug that number in. That's maybe not so reliable because you're talking to people who may or may not actually have the right understanding of your application and the fluids you're using and all that. So that's not ideal. The next thing people might do is just use a really approximate solution to get close. Again, that's not great, but if you can go in here and actually use the specific geometry that you have and do the full analysis, I think that puts you maybe at the level above. You'll be the resource for this kind of stuff rather than relying on calling the manufacturer.